Welcome to the deep dive. Grab a coffee, maybe dim the screen a little bit, settle in.
Yeah, it's definitely a good time to just sit back and focus.
We're going for a really relaxed, sort of late-night radio vibe today because we are tackling something massive.
Really massive.
If you're a software engineer, whether you're actively building in the AI space, fine-tuning models, or just, trying to wrap your head around how the tools you use every day actually work under the hood, this one is for you.
Absolutely. We're talking about the bedrock of modern AI.
Right. We are going back to the exact moment the technological tectonic plates shifted. We're unpacking a stack of notes on what is arguably the most important paper in modern computer science.
It really is the dividing line in the history of artificial intelligence. I mean,
Right.
you have the pre-2017 era and the post-2017 era.
Yeah.
Everything we consider cutting edge today traces its lineage back to this single document.
We are looking at a paper published to arXiv in June 2017 by 8 researchers at Google: Ashish Vaswani, Noam Shazeer, Niki Parmar, Jakob Uszkoreit, Llion Jones, Aidan Gomez, Lukasz Kaiser, and Illia Polosukhin. And they gave this paper a title that takes some serious nerve.
It really does.
I called it "Attention is All You Need."
The audacity of that title is what stands out first, honestly. In academic machine learning, titles are notoriously cautious.
Right, like an empirical study of whatever.
Exactly. Towards a better understanding of sequence models or something like that. This wasn't a cautious exploration at all. It was a literal structural claim.
A challenge, almost.
Yeah, they were telling the entire industry to take their standard architectural models, the ones they'd spent a decade optimizing, and throw them away.
I trust them.
No recurrence, no convolutions. Just one single mechanism. Pure attention.
So to really appreciate the cure here, we have to understand the disease. Let's set the scene before 2017.
Okay, let's go back.
If you were building a sequence model back then, say for language translation, you used recurrent neural networks, RNNs, and the underlying logic actually made perfect sense
Intuitively, yes.
because human language unfolds over time. We read from left to right, so the neural network should process data from left to right, one word at a time, continuously updating its hidden state.
It felt fundamentally correct because it mimics human working memory. You read a word, you hold it in your mesel buffer, read the next word, update that buffer, and so on.
Makes sense.
But from an engineering standpoint, this sequential dependency introduced a massive computational bottleneck.
The recurrence tax.
The recurrence tax, exactly. If you are computing a sequence of 1,000 tokens, you physically cannot compute the hidden state for step 50 until you have finished computing step 49.
It's an inherently serial operation,
100% serial.
which is just a brutal mismatch for modern hardware. GPUs are designed for massive parallel processing. They thrive when they can execute thousands of operations simultaneously.
That's what they're built for.
But RNNs force these highly parallel machines to process one sequential step at a time. It's like having a 1,000-lane highway, but only allowing one car at a time, leaving a massive amount of computing capacity completely idle.
And that serial bottleneck meant training these models was agonizingly slow. It severely limited how much data you could process, how large your models could get. But the hardware mismatch was really only half the problem.
Right, there's the memory issue.
The other half was a fundamental degradation of data over long sequences. Information from the beginning of a paragraph would literally fade away by the time the model reached the end of the paragraph. A giant game of telephone.
Wait, but didn't the RNN camp solve that memory degradation with LSTMs, long short-term memory networks?
They tried to.
Because they literally built specialized memory gates into the architecture specifically to hold on to that context, right? To pass it down the chain.
They did. And look, LSTMs were a massive improvement over vanilla RNNs. But they only mitigated the problem. They didn't solve it.
Ah.
Even with those clever gating mechanisms, the mathematical representation of the first word still has to be passed through 50 or 100 sequential matrix multiplications to reach the end of a long sentence.
And with every multiplication.
The signal degrades slightly. It's inescapable. By the time it reaches the end of the chain, the context is diluted.
Yeah.
It heavily restricted the context windows we could actually use in production.
Okay, so the status quo in early 2017 is a system that wastes expensive GPU hardware, takes weeks to train, and naturally forgets what it read a few paragraphs ago, despite our best engineering efforts.
A very frustrating time to be an AI engineer.
And then our 8 researchers step up with the radical pitch: self-attention.
Yes.
They propose throwing out the R and Ns entirely. Instead of reading left to right, what if every word in a sequence could look at every other word in that sequence simultaneously?
It represents a complete paradigm shift. Instead of processing a sequence through time, you process it through space.
Through space.
Yeah, every token looks across the entire input sequence at once and calculates an attention weight, basically determining mathematically how much does this other word matter for understanding my own meaning.
Let's ground this with the core reference example straight from the source material. Consider the sentence, the animal didn't cross the street because it was too tired.
A classic NLP problem.
As a human, you know instantly that the word it refers to the animal. Streets don't get tired. But how does a machine make that connection?
In the old RNN paradigm, the machine has to carry the mathematical representation of animal forward through the words didn't cross the street because,
Passing the baton.
right, updating its hidden state at every single step, like a really precarious relay race. And you just have to hope that the vector representation of animal survived that journey intact by the time it reached the word it.
And often it didn't.
Often it dropped the baton. What with self-attention, it's not a relay race. It's a group huddle. The word it queries the entire sentence simultaneously. It forms a direct mathematical connection to the word animal in a single computational step, regardless of the physical distance between the two words. No intermediaries.
Okay, but for the software engineers listening, forming a direct mathematical connection is a bit abstract.
Fair enough.
How is it actually doing that under the hood? If we aren't passing a hidden state sequentially, what is the actual mechanism making these words talk to each other?
This is where the paper introduces the concept of queries, keys, and values, or QKV. If you're a software engineer, the best way to understand this is to think of a relational database or a key value store.
Like a dictionary in Python.
Exactly, or a hash map.
Right. In a standard database lookup, you submit a query, the database compares your query against the keys, and if it finds a match, it returns the associated value.
Exactly. But in self-attention, it's a soft lookup. Let's look at the word it in our sentence. The network projects the embedding for the word it into three separate vectors: a query vector, a key vector, and a value vector.
Okay, 3 vectors per word.
Yes. When the word it is trying to understand its own context, it uses its query vector. It takes that query and computes a dot product against the key vectors of every other word in the sentence.
And the dot product is basically a measure of similarity. If the vectors point in the same direction in high-dimensional space, the dot product is a large number.
Right.
If they are orthogonal, completely unrelated, it's 0.
Precisely. So the query for it does a dot product against the key for street and gets a low score. Then it does a dot product against the key for animal and gets a very high score.
Because during training, the model learned that pronouns like it should heavily attend to nouns capable of the action in the sentence. In this case, being tired.
You've got it. These dot product scores are then passed through a softmax function to turn them into percentages that sum to 100%.
So animal might get 80% of the attention weight, street gets 5%, and the rest is distributed among the other words.
Yes. And finally, you multiply those percentage weights by the value vectors of all the respective words and sum them up.
So you're blending them.
Exactly, blending them. The result is a brand new context-rich vector for the word it that contains a heavy dose of the mathematical meaning of animal.
That makes perfect sense.
And the brilliant part is that this QKV matrix multiplication happens for every word in the sequence simultaneously.
Which means we've completely eliminated the serial bottleneck.
Gone entirely.
Because step 50 doesn't need to wait for step 49 to finish before it computes its attention weights. The entire mathematical process can be parallelized.
It's all just big matrix math now.
You can load these massive matrices onto a modern GPU and compute the entire sequence in one go.
You instantly unlock the full parallel compute power of modern hardware. This is what drastically reduced training times and allowed researchers to scale up models in a way that was structurally impossible with RNNs.
Unlocking the GPU is a massive win. But getting parallel hardware to process language introduces a glaring structural problem.
The order problem.
Right. If we process everything at exactly the same time, we've basically turned a structured sequence into a set, a bag of words.
It becomes completely permutation invariant.
Exactly. If I feed it the sentence, dog bites man, or man bites dog, the self-attention mechanism computes the exact same QKV relationships between those words, just in a different order. How does the model know the difference?
This was actually one of the biggest initial criticisms from the RNN camp.
Hmm.
If you throw away recurrence, you throw away the inherent concept of time and sequence.
You lose the left-to-right logic.
The transformer's solution to this is positional encoding. Before the word embeddings are even fed into the network, the model injects a mathematical fingerprint into each token that represents its absolute position in the sequence.
The paper describes using alternating sine and cosine functions, overlapping waves of different frequencies.
Yeah.
How does adding a sine wave to an embedding vector give the model a sense of word order? I mean, it sounds a bit like adding timestamps to a shuffled pile of vacation photos so you can reconstruct the timeline later.
That's a great analogy. Think of the embedding vector as a coordinate in space representing the word's base meaning. The positional encoding is another vector of the exact same size that represents the word's position in the sentence.
So you just add them together.
By adding them together, you are slightly shifting the word's meaning based on where it appears. They chose sinusoids specifically because of a beautiful mathematical property.
Which is?
They allow the model to easily learn relative positions. For any fixed offset, position k plus an offset can be represented as a linear function of position k.
So instead of explicitly telling the model, this is word number 4 and this is word number 7, the interacting frequencies of the sine and cosine waves create this continuous structured pattern.
It's a continuous wave of positional data.
The model can look at the mathematical interference between any two tokens and instantly calculate the relative distance between them.
Yes, it gives the network a highly structured way to understand distance without having to count sequentially. It completely solves the permutation invariance problem while maintaining parallel compute.
Okay, let's zoom out a bit and look at the actual blueprint of the machine. The paper details a structure consisting of an encoder stack and a decoder stack. Let's start with the encoder. The original architecture uses 6 identical layers stacked on top of each other.
Right. And inside each of those 6 layers, you have 2 main subcomponents. First, you have a multi-head self-attention mechanism. Second, you have a position-wise feed-forward network.
And there's some plumbing around those, too.
Crucially, yes. Around each of these subcomponents, they implemented residual connections followed by layer normalization.
Let's break that down. Multi-head attention. We just talked about the QKV process, but the paper didn't just do one pass of attention. They used 8 parallel attention heads, each projecting the data into 64 dimensions, giving a total of 512 dimensions.
That's right.
Why do we need 8 separate attention heads doing the exact same thing?
Because human language operates on multiple distinct layers simultaneously. In any given sentence, there are grammatical rules, semantic meanings, emotional tones, and structural relationships all happening at once.
So one head isn't enough.
If you only have one single attention mechanism, it has to average out all of those competing signals into one vector.
It would be like trying to listen to a symphony, but you're only allowed to hear a single averaged out frequency.
That's a perfect way to look at it.
By splitting it into 8 heads, you effectively create a panel of 8 specialized experts reviewing the sentence at the exact same time.
Exactly. And when researchers later dissected trained transformers, they found exactly this emergent behavior. Different attention heads naturally specialized.
Really? Like without being told to?
Completely unsupervised in that regard. One head might focus exclusively on adjacent words, capturing local syntax. Another head might span massive distances to connect the subject of a paragraph to a verb 3 sentences later.
That is fascinating.
They each perform their own highly specialized mathematical analysis, and then their outputs are concatenated together into a phenomenally rich, multidimensional representation.
Wow. Okay, so after the multi-head attention, the data passes through a feed-forward network. And as you mentioned, there are residual connections and layer normalization wrapping all of this.
Very important pieces.
For the engineers listening, residual connections, or skip connections, are essentially bypass shortcuts. You take the original input, skip it past the attention mechanism, and add it directly to the output of the attention mechanism.
Yes.
Why is that plumbing so critical here?
It solves the vanishing gradient problem. When you stack 6 deep layers on top of each other, the backpropagation signal, the math that actually updates the weights during training, has a long way to travel.
It has to go backwards through everything.
Right. If it has to pass through every single complex matrix multiplication, the signal can dilute to near zero. It vanishes.
Which means the earlier layers just stop learning.
Exactly. Residual connections provide a clean, unadulterated highway for the gradients to flow backward through the entire network. It stabilizes the training of very deep networks.
So you push your sequence through this 6-layer encoder stack. The self-attention lets the words share context, the feed-forward networks process that context-rich data, and the residual connections ensure the math stays stable.
That's the encoder in a nutshell.
The encoder builds a massive, heavily interconnected representation of the entire input sequence. Now, what about the decoder stack?
The decoder is structurally similar. It also has 6 layers, but it adds a third crucial subcomponent: masked self-attention.
Masked. The mask is such a vital engineering solution because if we are generating text translating from English to German, for example, we have a causality problem.
We have a major causality problem.
Yeah.
Think about the task of generating text during training. The model is predicting the 5th word in a sentence, and we want to compute everything in parallel.
Right.
But it should only be allowed to use the context of words 1 through 4. If the self-attention mechanism can see words 6 or 7, it's cheating.
It already knows the answer.
It's peeking into the future of the sequence it's supposed to be predicting. Because attention processes everything simultaneously, we have to artificially blindfold it.
So how does the math of the mask actually enforce that blindfold?
It happens right before that softmax function we talked about earlier.
Yeah.
We take the raw dot product attention scores for all the future positions, and we overwrite them with negative infinity.
Negative infinity.
Because in mathematics, when you pass negative infinity through a softmax function, it converts to exactly 0. So the attention weight for any future word becomes mathematically 0.
It completely severs the connection to the future.
Completely.
Yeah.
Ensuring the model can only attend to the past and the present tokens.
It is remarkably elegant. The encoder reads the whole document in parallel and builds a web of meaning. The decoder acts like a writer, generating one word at a time, looking at what it has written so far through the masked attention, and then consulting the encoder's deep understanding of the source material to pick the next word.
So they build this architecture. They ditch recurrence. They implement QKV self-attention, positional encoding, multi-head parallelization, and mask decoding.
And then they test it against the state-of-the-art RNN models.
The moment of truth.
The empirical results are where the tectonic plates actually crack. On the standard English to German translation benchmark, the transformer achieved a BLEU score of 28.4. That beat all existing models, including massive ensembles.
They crushed them.
On English to French, it hit 41.0.
The benchmark scores were state-of-the-art, yes, but the scores weren't even the most disruptive part of the paper.
It is the cost.
It was the computational economics of how they achieved those scores. That English to French model trained in just 3.5 days on 8 GPUs.
Yeah.
The competing RNN models were taking weeks of compute time on massive clusters to achieve worse results.
It's like Factory A versus Factory B. Factory A is full of skilled artisans carefully passing a product down a line one by one. It takes weeks. Factory B is a massive automated assembly line where 1,000 robots work on the product simultaneously.
And Factory B produces a better product.
Right. If you're an engineering executive looking at those numbers, the decision is made for you. You have a model that produces higher quality outputs, scales cleanly across parallel hardware, and costs a fraction of the time and money to train.
The adoption was practically overnight.
It was a massive disruption, and it had a profound sociological impact on the research community, didn't it?
It did.
Yeah.
There were brilliant researchers who had spent 10 or 15 years of their lives optimizing recurrent neural networks. They had built entire careers on intricate gating mechanisms and sequential training tricks.
Suddenly.
Almost overnight, a single paper rendered a massive chunk of that structural paradigm obsolete. Many initially pushed back, refusing to believe that you could process language so effectively without an explicit sequential memory.
It's hard to let go of a mental model you've championed for a decade. But you can't argue with 3.5 days on 8 GPUs.
You really can't. Math is math.
And the 8 authors of this paper didn't just publish and fade away. This single document launched an entire industry. Aidan Gomez left to co-found Cohere, Noam Shazeer co-founded Character.ai, Llion Jones co-founded Sakana AI.
The descendants of this specific architecture became the foundational pillars of the modern AI boom. By 2018, OpenAI took the decoder half of the transformer, scaled it up, and built GPT, the generative pre-trained transformer.
And Google took the encoder half and built BERT.
Exactly.
And from there, it's a sheer explosion. GPT-2, GPT-3, ChatGPT, Claude, Gemini, Llama, every single one of these large language models, the APIs and open source weights that software engineers are integrating into their code bases right now, is a transformer.
It's transforms all the way down. But the architecture didn't stop at language.
Right, which is what?
That is perhaps the most profound validation of the attention is all you need hypothesis. The architecture possessed such minimal inductive bias that it wasn't constrained to text. If you chop an image into patches, embed those patches, and treat them as a sequence, self-attention processes visual data at state-of-the-art levels.
Vision transformers.
Vision transformers, or VITs, they rival and often beat convolutional neural networks.
And AlphaFold too. Solving the 50-year-old grand challenge of protein folding in biology. They used a transformer-based architecture, treating amino acids essentially like words in a sentence.
We are seeing transformers in drug discovery, weather forecasting, code generation, music composition.
So if we synthesize the grand takeaway here, it comes down to what we call the scaling hypothesis. For decades, the instinct in AI was to handcraft domain knowledge.
Right. Humans trying to be clever.
If you were building a vision model, you hard-coded edge detectors and pooling layers. If you were building a language model, you hard-coded syntax rules and sequential memory gates. The transformer proved that handcrafting features is ultimately the wrong approach.
You don't need to be clever with handcrafted rules. You need a general-purpose architecture that gets out of its own way.
Just let the compute do the work.
Exactly. You provide a simple mathematical mechanism, attention, that makes virtually no assumptions about the shape of the data. You remove the hardware bottlenecks so it can scale infinitely across parallel compute, and then you just feed it massive amounts of data.
And it figures it out.
The model will figure out the relationships, the syntax, the edge detection, all on its own. The representations emerge naturally from the data rather than from human hard coding.
So what does this all mean for you, the listener? It means the tools you build with today exist because the industry realized that parallel compute and a simple, highly scalable attention mechanism could outperform decades of handcrafted sequential logic.
It changed everything.
The shift from recurrence to self-attention wasn't just a clever optimization. It was the unlocking of GPU-accelerated scaling. It is the architectural foundation of the AI era we are living through right now.
But this raises an important lingering question for us to think about. The true magic of the transformer is its minimal human inductive bias. It thrives by simply being allowed to attend to massive oceans of human-generated data. It learns the subtle patterns of our language, our art, our biology, purely by observation at scale.
Right, it needs that data to learn.
But as these transformer models generate more and more of the content on the internet, writing the articles, generating the code, producing the images, what happens when they run out of novel human data to train on?
The data wall.
What happens when a transformer is forced to train primarily on the outputs of other transformers? Will self-attention hold up when it is mostly attending to its own synthetic echoes? Or is there another paradigm shift waiting in the wings to solve that problem?
That is a fascinating thought to leave on, attending to its own echoes. We're going to wrap it up right there. Keep digging into the architecture, keep experimenting with those attention heads in your own engineering journeys, and we will catch you on the next deep dive.